Anjanaya, and Lavanya. Can we have a round of applause for them? Guys.
Recording in progress.
Can you connect this? How? Do you want to start? Hello. No, you start. Hello, hello. Good evening, everyone. Is this working? Yeah. Good evening, everyone. Our project today is transcontinental transmission, unraveling the impact of travel on viruses spread across continents. Our members. I'm Anjanaya, this is Reyansh, Sriram, Lavanya, and Antra. We have made this project possible only with the help of Professor Sugat, Sudipto, SLPs Ruchita, Karan, and Sedu. Introduction and background.
So our model is an attempt to simulate. Is it working? So our model is an attempt to simulate the case of a viral epidemic involving the concept of a metapopulation using a net logo model, and to potentially predict outcomes to help control such real-life cases. Now, this is a screenshot of our model. To make our model, we've used this programming language called NetLogo, and this is the NetLogo interface. So over here, we've got certain sliders. So these sliders can help us change the input variables of different parameters in order to change the starting conditions and in order to simulate different conditions. This is the graphical representation of our model, and what's happening here is that each individual dot represents a person. The white dot represents unaffected people, the blue dot represents vaccinated people, the green dots represent recovered people, and red dots, which you can't see any of over here, are the infected people. Apart from that, we've also got these 5 charts that show us the output, the result of our model. And we've also got a death counter that counts how many deaths, how many people died because of the infectious disease.
So there are 3 key concepts for this model. Communicable diseases. These are infections that spread from a sick person to a healthy one. Pathogens such as viruses, bacteria, and fungi cause these diseases. Metapopulation. Metapopulation is a group of separate populations of the same species which interact to a certain level but not freely. R naught. R naught tells you the average number of people who will contract a contagious disease from one person with that disease. The model and the test cases. Next slide. Yeah. So we have fixed parameters. Yeah. We have fixed parameters which contain of initial people, which will be the people at the beginning of the model, the initial amount would be 250. The infection chance is the probability of the people getting infected, which would be 40%, and the recovery chance is the probability of the people recovering in the given average recovery time, which would be 40%, and the average recovery time is 110 hours. The average isolation condition
tendency, which means that a person isolates themselves and the infection does not spread. The average isolation tendency would be 5%. The average hospital going tendency to get recovered would be also 5%, and the initial infected people would be 15. And the intra-mobility, which is the communication of people amongst the continents, inside the continent, would be 100%. And the variable parameters are the inoculation chance, which basically means that what is the chance of a person getting vaccinated and becoming immune to the virus. And the travel tendency is the ability to travel across the continents. We have 2 continents, and the ability to travel across the continents is adjustable. So those are the variable parameters and the fixed parameters of our model.
So this is a video of our model in action. And as you can see, all these people, they're moving around, they're contracting infections, and then they're recovering.
Yeah, so the hypothesis one is the number of death is inversely proportional to the fraction of population vaccinated in a linear manner. So our analysis, we have taken 3 test cases where the vaccination rate is from 0 to 100 with every 5 intervals. And we can see that it is inversely proportional as the death average reduces as the vaccination rate increases. So our result is, after running the model, we observed that the increasing number of people who are vaccinated, subsequently the death rate goes down. And there are some fluctuations which it's almost a linear relation between the 2 variables, and hence we can say that our hypothesis is correct. Over to Anjanaya.
Our second hypothesis was the extent of disease transmission is directly proportional to the amount of travel observed within a given time interval. This is our analysis. We took 3 test cases while increasing the travel tendency by 10%. We see that this chart is it shows no clear trend, and it shows a lot of fluctuation. Our result, there's a lot of fluctuation in the values of death rate, even though we have taken the average of 3 runs. There's no particular direction in which the death rate trends. There seems to be no obvious relation between the tendency of movement of people and the death rate. Although this seems counterintuitive, one possibility is there is some inaccuracy in the model due to which we did not get the expected results.
Conclusion, making this model provided us with a lot of useful information. We found out the relationship between the vaccination rate, and this is not a perfect model, and we realize our mistakes. Many simplifications were made in this model, but it is still a useful model to study the spread of infectious diseases.
Any questions?
Yeah, hi. Hey, very nice talk. I was wondering if you, I was a bit confused about the geographical area that you were considering. You mentioned that there are 250 people, but are those 250 people spread 1 kilometer apart from each other? Are they as close to each other as they are in this room? I was a bit confused about that.
So when we press the setup button on a model, it just randomly distributes the people across the continent. So there's no particular pattern in it. So we have a different setup every time.
Across an entire continent, so
Yep.
like across a very large area.
So we had 2 continents there, right? I'll just show you.
So it's just 2 separate meta populations. So it can be for anything. It can be between 2 separate continents, between 2 separate countries, between 2 separate cities. So like we can't simulate all the people in the city. We just then scale up that number.
Okay. I mean, yeah, it would actually be nice to try and fix the number of individuals to, I mean, instead of having 250 individuals, if you had a population density, for example, 200 individuals spread in 1 square kilometer or something like that, then what do you reckon your model would look like? Or what your results would look like in terms of transmissibility?
So like then obviously that would depend on the density of people that we've taken. But over here we've assumed that the two areas are equal and the number of people in both the areas are equal. So we've taken the same population density for both the continents, for both the separate meta populations.
No, right. I didn't expect you to answer that. I was just testing how far you would think. But good job, yeah.
Thank you.
Do we have any more questions? Okay.
This is working. Hi. Thanks for that really, really interesting choice of topic and great work. So this is more of a philosophical question, but you said that you found that your hypothesis was correct, right? So would you say that, or would you maybe say that you were unable to prove your hypothesis wrong?
I think we can say that our hypothesis was correct because, like we said that the vaccination rate would be inversely proportional to the number of deaths. So if we increase the vaccination rate, then the number of deaths would go down, and that's what we saw in the model.
Thank you, Pod 2.5. Can we have a round of applause for them? Thank you, guys. The second last presentation for the evening, we have a group called Gamma, where we have